Hello, in this video, we will be seeing whether a cycle exists in a linked list or not. We will be given a problem statement such that the head of the linked list will be provided to us and we have to detect whether a cycle exists, and if a cycle exists, we will be returning true, otherwise we will be returning false. Now, how do we go about with this problem statement? What we will do is use the Floyd's cycle detection algorithm to find whether a cycle exists or not. And to do that, we'll be using a hare. So let's say we have a hare and we are going to have a tortoise. Now, the interesting aspect here is that the hare will jump twice and the tortoise will be able to jump only once. So the thing to note here is for the tortoise, we are just allowing one jump in the linked list, and for the hare, we are allowing two jumps. And with this in mind, what we will do is both the hare and the tortoise, we will start at the head of the linked list that we are given. And then till the hare can jump to the next node, we will keep on jumping both the hare and the tortoise. And how that will look is something like this. So we are at the head position. We will say the tortoise will jump one position. So now the tortoise will move from the head position and it will come here. Whereas the hare that we have will be able to jump twice. So it comes and jumps here. Then from here it jumps to the next one. So the hare has reached here now. Then again hare can jump next. We will jump the tortoise by one position. Tortoise will come here. The hare will jump two positions. So 1 and 2. So jumping from 1 and then going back, it comes here. Then hare can still jump ahead. So what we will do is move the tortoise one step ahead. So tortoise comes here and then hare again will jump two positions. So from here at the node 2, 1 and 2, and it reached here. Now we can see that both the hare and tortoise have met one another. This indicates that there exists a cycle in the linked list, and that's the core idea of this implementation of Floyd's cycle detection, wherein one entity will jump slower in comparison to the second entity. So if one entity can jump once, which is the tortoise, the second entity, which is going to be the hare, is going to jump twice. And if at any point in this jumps they are able to meet, that will mean that there exists a cycle. And that's pretty much in terms of the logic aspect. Let's dive into the code aspect and see how it will look in JavaScript. First, we said we are going to need two entities. So one entity is hare, let's say, and the second entity is a tortoise. Both of them will start at the head position of the input that we have received. So this is the head of the linked list that we are going to be receiving. And both of them have the same starting position. We will say head is equal to tortoise is equal to the head. So both of them now start at the head. And edge case, we will say if you're not able to detect a cycle, that means you're not going to have a cycle in the end. And to detect a cycle, we will now again say that whether the hare that exists can jump. So if while the hare exists and the hare can jump, so I will say hare dot next exists, then we will perform this operation of jumps. So we will say the tortoise can jump one step and the hare that we have can jump 1 plus 1, which is going to be 2 steps. And if at any point both the hare and the tortoise meet one another, that will mean that we have found a cycle. So we will just say if hare and tortoise meet one another, then we just return true. And that's pretty much the conversion of whatever we covered so far of this Floyd's algorithm of cycle detection into code. Now that we have covered the code aspect, we will jump into the time complexity aspect. Let's say scenario 1, wherein there is not going to be any cycle. If there is no cycle, then the hare will basically keep jumping towards the end of the input that we have received. So if you have n nodes, the time complexity in that case would be n. So let's say the time complexity that we are going to have in the case of no cycle is just going to be big of n, because let's say we assumed having n nodes. Now let's say we have cycles. Now when we went through the logic aspect, we started at this position of the head, both the hare and the tortoise. And once you reach the end, when the hare reached the end node here, it was able to proceed ahead and keep on jumping ahead. And it went on keeping on jumping till they finally met. So you basically said that the jumps that were required were until the hare and the tortoise were able to meet. And let's say this finite number of jumps that will be required will be k. Then we can just say in worst case, so in the good case when there is no cycle, it will be big of n. In the worst case, the jumps that are required, which are going to be limited, because if there is a cycle, the tortoise and the hare are going to meet at some point in time as we continue this jumps. And let's say these jumps are k. So we will say burst time complexity will be big O of n plus k. And in terms of the space complexity that is going to be required, it's going to be big O of 1. Why big O of 1? Because we are just using 2 pointers here, and we just keep on incrementing the position of these pointers in the linked list by using the next pointer. So we will just keep on jumping both the hare and the tortoise until we reach the end of the linked list, which is pointing to null, or we have found a cycle. And that's pretty much it in terms of implementation. Thank you for watching. Please like and subscribe.